Now, we saw in the last video that we were able to make a linear interpolation, which was okay. It wasn't all that great. It got us within 13%. And then we saw a quadratic interpolation of an exponential, and it got us below 1% of error. So we would assume that if we were to keep going up in order, that we would get an even better approximation of values if we knew some values that were on the curve. And so what if we wanted to get that third, fourth, fifth order? Okay, so what's the algorithm for that? And that's what we're going to look at in this video is what is the algorithm for being able to work with general Newton's interpolating polynomials? And similar to what we saw for the quadratic, what we're going to do is we're going to find the secant slopes of the previous secants. And it's almost, in fact, it is a recursive sort of algorithm in which what we're going to do is we're just going to use the previous secants to find subsequent secants of the next orders of the polynomial. So now you remember our friend b1 and our friend b2. So this is just the very first coordinate of y that we're given. This is going to be the first slope between the first y's and dividing by the first x's. And then we use the slope of the slopes. So this was the slope between the next two x's and y's divided by the previous slope. And we're just going to keep doing that. Okay. Now, obviously, the higher order we have, the more of these we're going to have to do. So this is how we're going to define it. Okay. So this is just Bn suggesting that it's going to be the secant of all of those previous secants averaged, if you would. All right. And so each time we have this recursive process, we're getting these finite differences. All right. So this is our first finite difference. And this first is actually going to be the coefficient of B1. And then we're going to use all of the others. And this, by the way, this is for a third order polynomial when we know 4 points. We're just going to go ahead and find all the secants. And then we're just going to find the secant of the secants to derive the third. And we just keep doing this until we get all of them. Okay. So again, it's really just the numeric process of number crunching. We just want to make sure that we keep it in order. So we're going to take a look at an example. We might have to split it up into 2 videos, but that's fine. Just to understand how well this actually works. Some of you may have seen, and I remember when we teach differential equations that we look at Bessel functions. Bessel functions are very, very useful for us for solving particular types of differential equations with non-constant coefficients. And a Bessel function of the first kind is defined as j sub 1x is equal to this mess right here, this infinite power series. All right. It's not pretty, let's just say that. And it's actually an infinite sum, so we'd actually have to take the limit as it goes towards there to be able to try to figure out what the value of j sub 1 is when we substitute values of x. But let's say for some reason somebody went through and they found some of the values of the Bessel function, and they knew them, all right? So maybe they knew 5 points, and these were the corresponding values of the Bessel. So because we have 5 points, we're going to create a fourth order Newton interpolating polynomial. Okay, so we'll say a fourth degree Newton interpolating polynomial. And we're going to find for J1 using the points above. And then we're going to approximate numbers in between. So let's approximate 1.9, 2.1, 2.3, and 2.5 using the fourth degree polynomial. Then we're going to compare it using MATLAB. And MATLAB has a function Bessel J, where if of the first kind, you could just substitute back in for x. So if I wanted to know the exact value of Bessel J first order at 1.9, I would just substitute 1.9 in for x. And then we're going to find the percent value. We'll print them in a table. And then finally, we're going to create a couple plots. All right, so let's plot the overall Bessel function and then the Bessel function with the interpolated plots. And we're going to hope that the interpolated plots are pretty close, if not on the Bessel curve. All right, so let's get to this. All right, so and this isn't an easy problem because we have a fourth degree polynomial, meaning we have 5 points in here. So let's start by defining. I'm going to define a vector, and I'm going to call it x. And these are our x coordinates: 1.8, 2.0, 2.2, 2.4, and 2.6. And I'm going to call this j. I'll just call it j1. I'm going to make it lowercase j just for ease of use. And those are going to be the corresponding values, the 0.5815, and then 0.5767, 0.5560, 0.5205, and 0.4708. All right, so now we need to create a fourth degree polynomial, which means that we are going to go ahead and start by saying B1 is going to be equal to our very first y value, which in this case is J1 of 1, right? So that's really easy. Now, I'm going to call this B21, okay? So this is actually, and I'm going to bring this back, this is going to be the first secant, okay? So that, and that's what we're finding, is we're finding the first secant as we go through here, all right? So that's going to be equal to y2 minus y1, so it's going to be J12 minus J11 divided by x2 minus x1. All right, and that's going to be the coefficient of the linear term. All right, now, of course, that just found the slope between these 2 points right here. We still have to find the slope between these two and these two and these two. And if we look at our diagram, what we're doing is we're actually just going right down the line. All right, now, this is going to be a little bit painful at first, but can't we just cut and paste? And we're just going to change some numbers. All right, so let me call this B22, B23, B24. All right, and I'm just going to change this to 3, 4, 5. All right, and notice how easy this is. I'm just going right up the line, just changing it nice and easy to make it really easy for us. And then I'm just going to change these to 2, 3, 4. So these are the successive secants. And I'm going to change this to 3, 4, 5. And change this to 2, 3, 4. All right, so we're actually, these are all the first order finite differences. But of course, now we need the second order finite differences. So I'm going to call this B31. And if we take a look at our diagram that we had from before, we are going to find the secant of the previous two secants. So this is actually for us going to be B21 and B22. And the span is going to be from x1 to x3 down. And then we're going to have x2 to x4 and then x3 to x5. All right, so for B13, I'm just going to take B22, which was our first secant, minus B21, which was our second secant, and I'm going to divide that by x3 minus x1. All right. And just like before, I'm just going to copy and paste these. All right. Now I'm getting one less because I'm going to use 2, 3, and 4. All right. So we should always have, each time we're doing this, we should have one less secant that we're dealing with. So I'm going to say this is 3 and 4. And this is 2 and 3. And then I'm just going to change these numbers. 4, 5. And then I'm just going right up the line. All right. So that's going to be, and I'm just going to change these because we would be redefining each time. Have to do it again. All right. But it shouldn't be too bad this time. So I'm going to get B41. And that's going to be equal to B32 minus B31. And now our span, if we look at our chart for our third order polynomial, it's going to go from 4 to 1. All right, so each time we're just increasing the span of our finite differences. All right, so this is going to be x4 minus x1. And then we can cut and paste this guy, and we can have a B42, and it's going to be B33, B32. And then we're going to change this to 5 and 2. And then even though this one isn't on our table, now we can have B51. And B51 is going to be equal to B42 minus B41. And we're going to span the entire span of the x's. All right, so that's going to go 2.6 minus 1.8. Okay, so these are the coefficients. This is B1, B2, B3, B4, and B5. Now, if we go back to our formula for the interpolating polynomial, B1 is the constant, B2 is the coefficient of linear, B3 is the coefficient of quadratic, B4 is going to be the coefficient of cubic, etc. And notice that we have x minus x1, x minus x2, x minus x3, just depending upon what the order is. Okay, so we should have, if this is going to be our quadratic, then we're going to have two terms in it. Okay, so now a good way to do this is that you don't type in the entire polynomial, you just type in part of it, and then you can go ahead and redefine it and add the rest. So I'm going to call this F4. That's going to be equal to B1 plus B21 times x minus x1 plus B31, and I'm going to say times x minus x1. And we might need some vector operations, so I'm going to say dot times x minus x2. Right? And then plus B41, and after this one I'm going to stop and I'll show you the trick that I was talking about, times, and I could just copy this because it's the same as before, and I'm going to say dot times, and another parenthesis there, and then dot times x minus x3. All right, now this is a third degree polynomial at this point. So what I'm going to do is I'm going to say F4 is going to be equal to F4 plus. All right, so I still need that last term in here, but it's just starting to get too long. For readability, I'm just going to copy this. Right, so this is our last term. So plus B51. And we have x minus x1, x minus x2, x minus x3. And surprisingly, we are going to have x minus x4. Now, this is our function. All right, this is actually all of part A, just to model this Bessel function. So it's a long way of doing this, but this is our algorithm. I'm going to run it just really quickly to make sure I'm not making any errors. All right, and since I said x minus x1, I'm going to have to clear out x at some point. All right, but those numbers look pretty close for F4, and they should, to what we had from before up here. All right. Now, let's see what's going to happen. All right, if we go to estimate this. So that was part one. All right, so create a fourth degree polynomial. And now we're going to use the polynomial to approximate J 1.9, 2.1, 2.3, 2.5. All right, so now what I'm going to do is I'm going to create a new vector. I'm going to clear X because we've already used it. And now I'm going to define X to be, well, that's our polynomial. Let's do this. So maybe what I can do is I can say that this is x1. So let's do that. Let's just change all of these x's to x1s and make like a Sims variable. It's a bit of a pain, but. And I'm going to make a Sims, just so I'm not redefining, because I am going to use x again. So let's make a Sims of x1. All right, and let's run that just to make sure that nothing fishy is going on. All right, and we're going to do an fprintf. We're going to say the fourth degree polynomial for J1 is %s, and we're going to call F4. All right, so now this should be a really long polynomial when we run it. All right, and here it is. All right, so it's not pretty. All right, but it is what it is. Okay, so boy, that's pretty long. So let's see what happens with this, because now we need to substitute. Okay, so now what we're going to do is we're going to substitute for J19, J21, etc. So now we're doing part B here. All right, and then after we do this, we'll just flip to another video so we can do the rest of this. So we're going to use a polynomial to approximate J19, J21. So I'm just going to go ahead and make a new matrix. All right, and I'm going to call this matrix X2, and that's going to be 1.9, 2.1, 2.3, 2.5. And what I'm going to do is I'm going to say y2 is going to be equal to, when we substitute back in for f4, and we're substituting, the old variable was x1, and now we're substituting x2 back in. All right, now this should work because I defined each of the multiplications between x's to be vector multiplication, or I'm sorry, not to be scalar multiplication, but to be vector multiplication. All right, so let's just run it just to make sure that works. All right, and it looks like it's giving us some values out of here. Okay, so that's pretty cool. Now we have no idea what these are. All right, so we're going to make a for loop and we're going to print those out. Okay, so we're going to say for I equals 1 colon, let's just say length of x2, which is 4, we know, but just in generic terms, we're going to f print f, and we're going to say the f4 approximation for j1, and I'm going to say j1% f. All right, and let's do this. Let's say j1% 2.1f, since I think 2.1 is going to give us 2 significant digits with 1 decimal place, is, and let's just say %f and \n, and that's going to be x2i. All right, so that's the ith element in x2, comma, y2i. All right, and then we're going to end this. All right, so let's see what happens here. This should be our estimations, and that way we don't have to worry about the approximations any longer, or the exact values. All right, so these are the approximations. All right, and we have our polynomial. Now, if you look at this, we already kind of know whether it's going to be close or not, because this is our estimation 0.581176. 5815. So we're actually really close to this, which is really cool for us. All right. Now, in the next video, what I'm going to do is I'm going to finish this off, okay, because we've just gotten to the point where we've just done a lot of stuff. But the next video, we're going to find some errors, and then we're going to look at the graph and see if they fall on the polynomial, and also if they fall on the original Bessel or they do not.